Okay, take a look real quick. I want to show you something here. Did I show you guys how to take sums on your calculator?
No.
Yeah. With the sigma stuff?
No, but I know that.
Okay, so I meant to. I kind of forgot that. I need to show you that too. Remind me. Don't let me leave today without showing you that. Okay, so take a look at this picture up here. I'm going to show you, explain the second fundamental theorem of calculus, which is really a very, very simple one. Not a big deal. But to get this, we gotta look at an area under curve in a little different way than we have. Okay, so imagine that we've got this area under the curve F that is anchored at A. It starts at A, but instead of ending at some fixed point, let's say it ends at a variable point. It ends at X, and X can change. Do you see that that area under that curve then is a function of X? Does that make sense? And when we talk about something being a function of X, all that really means is that it changes as X changes, right? Do you see what I'm saying? In the past, what we've talked about up until now, we've always talked about areas under curves from some constant starting point up to some constant ending point, and that represented some number, right? A definite integral. You'll notice, and you haven't had a ton of experience with this, but you're accumulating experience. Definite integrals, the answers are a number, right? It's an area under a curve. Different than antiderivatives or indefinite integrals. Those are different, right? Those are families of functions. Those are different. An antiderivative, remember, that's calculus Jeopardy stuff. When we solve an antiderivative, we get back the family of curves that I could take the derivative of to get the integrand, right? So totally different stuff, although it turns out they're related, strongly related. Okay, this is slightly different than the definite integrals we've talked about, though, because it does end up depending on X, right? So we could call this, if we want to represent this area in here, let's call it capital F of X, okay, and it is a function of X. Now I could write that maybe in this form. So my upper limit is going to be an X, and the shape of the curve is determined, under which we're adding up that area, is determined by the profile of this other function. Call it little f. Right? We're looking at the area under this curve, little f. A lot of times the way that we deal with stuff like this is we'll introduce what's called a dummy variable. The dummy variable is t, and this is, you could make it an x if you want to, but to make it an x is a little bit confusing in a way, because x we're defining as the place where we're stopping the area, right? Now that's sliding. That x value might be sliding, but still that variable represents the upper limit of the moving variable, upper limit of our area, right? And so we need to put that at in the upper limit of our integral. Right, so it's got to go there. So then what variable goes inside the function? Well, that's the job of the dummy variable. What the dummy variable's job is essentially to do, it's a scout. We're going to put in values of t just to see what this function f looks like, right? We got to know, we have to be able to see what the territory ahead of us looks like as this area slides in this direction. We got to know what the shape of this curve is. And so the dummy variable t, those are just the values that we're plugging into the function to see how high it is for various different upcoming values of x. Does that make sense? Yeah. I mean, so t, we could call it x, but we're just calling it t because we're going to put in all the infinite possible values maybe of t just to see what this curve looks like, so we can see what the upcoming area is going to be as x changes. Okay? So it's really just there to kind of hold a place. But X, remember, is determining where we actually do stop, the value of t that we're going to stop on to determine what the area is. Okay. So let me throw it open for questions or things you want clarified about that. Or this is kind of a,
we do one with like real numbers.
well, yeah, we will, but honestly, there aren't going to be a lot of real numbers here. Because where we used to have numbers, now we've got a variable upper limit. Now what we will do is this function f will be something like maybe a polynomial or a sine function or something. So it won't just be this general function f, it'll be actually a function. And we'll look at some examples like that. But my question to you is then, if I were to try to differentiate this thing, you might wonder, why are we we don't even know what this thing is yet. Why are we differentiating it? What if we wanted to find the rate at which, oops, it's not t. What if I wanted to find the rate of change with respect to x of this area function that we've developed? What's your thinking about that? And think what a rate means. The rate just means how much is the area changing as x changes. Now what's going to determine that? As I inch this x forward this way just a little bit, and I advance it just a little bit, and I add a little bit of extra area, what's determining for every little increment that I move this thing forward, every little change in x, what's determining, say it again? The height of the curve is really what's determining how rapidly we're adding area, isn't it? Right? Does that make sense? Okay, so doesn't it make sense in a way here that if f of x is defined in this way, that the answer to this really has to be f of x? Right? Does that make sense? What's determining the rate at which we're adding area is the value or the height of the function at x. It's f of x. Okay? That's the second fundamental theorem right there. That's all it says. It just says, and literally, here, let's just write it down. This is what it says in the book. The derivative with respect to x of the integral of f of t dt from a to x equals f of x. If f is continuous on some open interval I containing blah blah blah. You know, if the function it doesn't explode or do something weird. So for a smooth function. Okay. That's it. Okay. So that's the picture right there that kind of tells the story, right? The rate at which the area is increasing unless it's below the x-axis, I guess, is determined by how tall the function is there. The taller the function is, the more rapidly we're accumulating area. So let's try a problem. And you'll see that these problems are really simple. There's nothing to them. So what's the answer? Say it again. Not that it's not even that difficult. It's just going to be what's f in this case? Oh, okay, so this is f of t right there, isn't it? Right? And the rate at which we're accumulating, the rate of change of this area, because this whole thing, remember this whole thing right here, just represents area, right? The rate of change of the area is just that. It's just the value of that function at x, the height of the function. Here, so all we're doing is we're just plugging x in and finding out how big it is at x. Okay. Make sense? Okay. What's the answer if I do this? Now watch closely. What if I make this lower limit negative 1 million? Doesn't change it, does it? It just means now that there's already a whole big area there. The amount of area that's there is irrelevant. What we're asking about is how fast is the area changing? And the area is being accumulated at that rate, right? It doesn't matter how much area we've already added up. We want to know how fast it's changing at x. And that's how fast. Okay? All right, so that's all the book talks about. But there's another one I want you to be aware of too. And that's that handout I gave you. And this handout, by the way, this is kind of the name I just invented for this because it's not something that shows up in textbooks, but it works. This really does work. And so I think it's a safe name to call it. This is a generalized version of the second fundamental theorem. And here's how it works. What if we have the derivative with respect to x of, same kind of a deal, of a definite integral of some function f, f of t dt, just some, we don't know what the function even is. But this time, instead of stopping at x, we're going to stop at some upper limit determined by a second function, g of x. Okay? Now think what that's saying. That's kind of a brain twister a little bit, isn't it? Now, what that's saying is that instead of adding up the area under this curve and finding that as a function of this variable stopping point x, we're going to have the stopping point itself be a function of x. So for example, what if it were the function x squared? The stopping point were the function x squared. As x doubles, then what's that doing to the stopping point? Well, it's making the stopping point move forward by a factor of 4, right? And so where we stop, the stopping point is kind of accelerating along the x-axis. The further we move along, the bigger the x value, the way further down the actual stopping point is going to be for our area. Okay? Weird concept, right? But we can do stuff like that. We can have a function of a function. Okay, so then how is this going to affect our answer, right, if we want to differentiate this? Well, here's what it does. Now, instead of just having f of x, well, this would make sense for us now to have f of g of x, right? Because it's going to be the height of the function at g of x. But we also have to take into account, as x is changing, how fast is g of x changing, right? Because g of x is not changing linearly. If g of x, for example, is x squared, as x increases, g of x is increasing more and more and more rapidly, right? And so we also, it has to be a chain rule kind of thing. We also have to have in there, we have to have the value of the function at g of x, but we also have to take into account how fast that endpoint is receding, and we have to multiply by the derivative of g of x. How fast is g of x changing with x? That's pretty hard to conceptualize. I think if you think about it a whole bunch, you can do it. But you have to really kind of, this is one of those things in calculus, and these things start to become more and more frequent as you go further in math. I remember doing this lots of times in college, and thinking, wow, going home at night, just thinking about this stuff and just thinking and thinking. And finally, you kind of go, oh, yeah, well, okay, now I guess that kind of makes sense. But it takes a long time to wrap your brain around some of these concepts. I don't think it's super important that you even do get a firm comprehension at this point of what that looks like in terms of a function. I mean, using it's really simple. And I'll demonstrate an example of how you can do a problem. It's a piece of cake. But trying to kind of get an idea of what that problem represents in terms of a function is just a little bit tougher. But when you get a chance sometime, when you get some downtime, just think about that one a little bit. Think about what this really means. Okay, so so here's an example. Take a quick look at one. Here's the example that I gave you on this handout. Let's just take a quick look at this one. So here's that generalized second fundamental theorem. Let's take the example that the area function f of x is just going to be the integral from some pi, some constant, up to, in this case, secant of x squared. That's going to be our function, our upper limit that's a function of x. And we've got this seemingly, this looks like a really hard problem, doesn't it? It looks horrible. The argument here, the function is sine of the square root of cosine t plus t cubed. My gosh, that looks just grisly. It looks so hard, right? It looks like nothing you ever want to touch with a 10-foot pole. But it's not that hard, right? Because if we want to differentiate this thing, and that's what the question is asking for, what's the rate of change of this area function, the derivative with respect to x, all we do is we just evaluate this integrand at secant of x squared. So every place I used to have a t, I'm just going to plug in a secant of x squared. No big deal, right? And then I just have to multiply by the derivative of secant x squared, right? This is just going to be if g of x equals secant of x squared. This is good review for us. What's g prime of x? Yeah, I've already got secant of derivative of secant hand is secant hand, tangent hand, right? By the chain rule. So I get secant hand, tangent hand, times, and if I fill in the hand, it's an x squared. If I apply the chain rule, and I look inside the secant function, the derivative of x squared is just 2x, right? Make sense? And so there's my secant x squared, tangent x squared, 2x. There's g prime of x. That's not a hard problem. It's actually, probably the simplest kind of problem you'll see for the rest of the year is the second fundamental theorem kind, because it's so short. There's very little to do. I get the sine of all that stuff times g prime. And then if I wanted to clean this up, I could put the 2x out front and pull the secant squared, tangent squared out front. And then I got this ugly part, sine of that big argument. But that's it. You could even take this one step further if you wanted to. The ultra generalized second fundamental theorem just says that now what if you had the area changing on both ends of the function. The lower and the upper limit were both functions of x. So on the lower limit, we had this h of x function that's determining how fast the lower limit is moving. This g of x function that's determining how fast the upper limit is moving. And so now that's kind of a complicated picture we've got built there. We've got something like, there's f. Down at this end, we've got what's determining where the lower limit is going to be. Is this function h of x, which is moving left and right in some weird way. We've got this upper limit that's g of x that's moving left or right or some combination as a function of x. And so this thing's accordion oscillating all over the place, right? But if we want to know how fast as a function of x this area is changing, then all we have to do is we're just going to take the first fundamental or the second fundamental theorem as we normally would of the top limit minus the second fundamental theorem at the lower limit. Right? So it's just going to be alpha of g of x times g prime of x minus alpha of h of x times h prime of x on the bottom. And that's a pretty advanced problem. I mean, I don't think you'd never see anything like that on any standardized math test you'd take. And there's no way that would ever show up on an AP test or anything, but you might see that eventually in college. So there it is. Hang on to that. I attached this to the Moodle calculus site too, if you want to print it out or something. And all this site, by the way, just so you know, at the end of the year, I'll try to make sure everything's loaded up on this Moodle site, all the stuff that we've had, all the handouts. And I'll just put a little section at the bottom where all that stuff will just sit. So if you're in college, if you ever want to, you can just keep your accounts. If you ever want to access this stuff in college, you're obviously welcome to come back and get on the Moodle and download anything you want to. So, all right, questions? Does that make sense? Much is going to make for now? Yeah. All right. Okay. I think we can. What's that? Oh yeah, the calculator stuff. Thank you. Yes, I need to show you that. Good, good.
Good call.
Yes. Okay, let me pull that up. Okay, so yeah, take a look here on the calculators. This is really handy. You can use these calculators to add up sums. It's complicated a sum as you want to. Like for example, let's just say we want to. Here'll be our little test problem. Let's say we want to add up the sum of sine of I squared plus 2 as I goes from 1 to 121. Here's all you have to do. It's so simple on these new calculators. It used to be harder, but now it's really easy. And you guys might have to remind me, because you've probably done this more recently than I have, but I think you just go to math, and then you go to 0. Is that what it was? You said it was?
Yeah.
Down to the 10th option. There it is. Oh, look at that. Okay, so you just go math 0. And oh man, look, this couldn't be easier. It used to be you used to have to do sum of, sequence of, and put all these things with commas in there. Now it's so simple. It just looks like a sigma. So what's going to go there? I could make it an x, or I could even make it I here if I want to. And I would encourage you to maybe even do that, because then it does look like an index variable. So to get I, all you do is just go alpha hij. There it is. Okay, alpha I. So I goes from 1 to 121. And then in there, I'm just going to put a function of I. And maybe x is easier, because then you can just hit the x. That probably is easier to do. In fact, I'll do that. Let's make it an x. Okay, so then I would just do sine of x squared plus 2. And I do want to make sure that I'm in radians mode, which I am, so that's good. Okay. And I think that's it, isn't it?
Yeah.
If I hit enter, it's going to think for a second. It's going to tell me the answer. About that. Ken, have you tried doing limits on this? Does it let you do limits on these two? Let's try something real quick. Let's just mess around. Now the 89s you can do this stuff, but I don't think you can on here. I do, yeah. No, never mind. Failed attempt. Okay, does that make sense? Okay, so you can add up signals. It doesn't have to go from 1. You can make these go from any lower limit you want to. Okay. I think, well, no, never mind.
How do you do it on the?
On the 83, okay, on the 83, you go like this. You have to go, let me see that for just a second. Anybody else using an 83 that wants to not do this? Because if not,
You don't have all that.
nobody else? You're welcome to, anytime you want to, though. Okay, let's just see if we can get a lap real close.
There's some stuff on it.